All right. Hello. So today I'm going to be going over the Mr. Pabico test number 3 practice questions that he sent out today. I wasn't here in school today because I'm currently a little bit sick. Actually, not really a little bit, but yeah. But I'll be explaining some of these problems. I don't have them typed up here because I just got sent a photo of them and I don't feel like typing them up that much. But yeah. So the first question is saying, uh, family of 4 people with a total mass of 200 kilograms steps onto a 1,200 kilogram car. The car spring compresses 3 centimeters. So we can look at this as here's a spring, here's a car. I'm going to label it as 1,200 kilograms, and then here's a mass of 200 kilograms. So these are the people. So basically, the springs are already going to be compressed a certain length before the people step on it. But then it's saying that it compresses 3 more centimeters. So it was here, all the people step on it down 3 centimeters. So when we look at this problem, I don't think it's necessary to worry about the state of the spring before because how spring constants work, basically, regardless of whether it was, regardless of whether this 1,200 kilograms was there or not, the spring would still only compress 3 centimeters when 200 kilograms are placed on it, assuming it's an ideal spring. I know we don't actually see that really happening in real life, but that's fine. So the first thing I want to do for this problem to get credit, I'd assume, is to draw a free body diagram of the 200-pound mass, set of axes. So pushing up is a normal force, pushing down is mg, and then the spring is also pushing up, I guess, with a force of negative kx. And I guess if this is a negative kx, then our axes upward would actually be negative. So now if we set up a force diagram, oh, by the way, it's asking us to calculate spring constant. Sorry, didn't mention that. So if we set up a force diagram, the sum of the forces is equal to, I'm going to say mg minus kx, and it's not going to be moving there, so I'm going to say mg equals kx. Only thing is, I think it's supposed to be negative. I think I might have set up this wrong, and they're supposed to be in the same direction. Whatever. Basically, we have this relationship of mg is equal to negative kx. Mg minus kx. Okay, whatever. Yeah, I don't think these signs are too important for this problem, but basically the mass is going to be 200. The what are the other values? The gravity, sorry, I was going to calculator, is 9.8, and then we're solving for k, and then x is, I'm going to keep an absolute value here just so people don't get mad. Um, 0.03 centimeters, 0.03 meters, sorry. So to solve this, k equals 200 times 9.8 divided by 0.03, which gives a very, very, very large value, which, you know, I'm a little bit concerned about that. Okay, whatever. So, is this real? Okay. 653, 3.3 newtons per meter. So this is a very, very, very large value. I guess that would make sense given it's only compressing 3 centimeters with 200 pound or 200 kilograms on it. Sorry. So, yeah, that does make sense, I guess, for the first problem. Okay. And so for part B, it says, suppose the real spring constant was 15 newtons per meter. How far will the car loaded with 300 kilograms. Okay, so here we have 300 kilograms, and we have a still a 1200 kilogram car. The weight of the car isn't actually too important for this problem, and I think it's just there in part to scare us. But basically, it's at this height and it's compressed a distance x that we're trying to figure out. So let's see, how far will a car lower if loaded with this much? So let's set up our equation. How about, so again, we have mg equals negative kx. You can draw a free body diagram, whatever, 300 kilogram mg, pointing up, bn. It's being held up by the spring constant, so you could also put that. And we're given a spring constant of 15. So m is 300 times 9.8 equals negative k. So I'll just divide it by k, which is 15. That's a distance x, and it's going to be a negative distance because it's going downwards, assuming this is a positive. So 300 times 9.8 divided by 15. I'm a little bit concerned that I did that wrong. Um, Whatever. I think this is correct if I'm not mistaken, because 50 newtons per meter is not a definitely not a very strong spring. All right. Well, it according to this would go down 196 meters. To put that into perspective, the amount of kilograms being, or the amount of newtons pushing down on here is going to be 300 times 9.8, which is basically 3,000 newtons pushing downwards, and this spring will push up and I guess compress 1 meter for every 15 newtons. So that does make sense in that case, but also very interesting. So yeah, so that's gonna be it for the first problem. Second problem says a single simple pendulum on the moon with a gravity of 1.62 meters per second squared is set into simple harmonic motion. Period is measured to be 1 second. So I'm gonna assume the pendulum is a small angle, or or approximately an angle less than 30 degrees, and send to simple harmonic motion. And the period is 1 second, and the gravity in this case is 1.62 meters per second squared. So it's asking to calculate the length of this string L. So for approximating with small angle approximation, you can say that 2 pi over t equals root g over L, and then we're just solving for L. Easiest way to do this, I think, would be to maybe square both sides. So we get 4 pi squared over t squared equals g over L. G over L, and then flipping that around, we get L equals g t squared over 4 pi squared, and g in this case is 1.62. So 1.62 times 1 squared divided by 4 times 3.141 squared. Because I could also use pi squared. And the length, I have no idea what is going on right now. I feel like all these are like, yeesh. feel like I might be doing something wrong here because this is not a typical length. Let me just check my algebra here. So 2 pi over t equals g over L. Squaring both sides, we get 4 pi squared over t squared equals g over L. And then I'd shove all this onto the bottom, replace that since g over that, t squared goes to the top, yeah. Okay, well, then that makes it 0.041 meters in terms of the length. Um, this period is measured to be 1 second. Swing back and forth 1 second. All right. Um, sure. That's good enough. Okay, so now it's saying it's brought back to Earth, brought down to Earth, and send a simple harmonic motion. What is its measured frequency? So now we're going to be using the relationship 2 pi f equals root g over L, with g being 9.8 and L being the L we calculated at 0.041. Hopefully that's right. And then basically to get rid of the 2 pi, we just divide by 2 pi. And so the frequency is square root of 9.8 over 0.041 divided by 2 pi, which is frequency equals 2.461 hertz. Hopefully that is close to right. Whatever. Okay. So the next problem is saying how do destructive and constructive interference differ. So destructive basically means that there's one amplitude that's positive and heading at one amplitude that's negative. When they meet, they're gonna like cancel out, basically make a smaller amplitude than their combined, or they're gonna make up their combined amplitudes, but smaller than either one of these, right? And then constructive is where they increase their amplitude overall. So yeah, I'm not gonna go into detail about that question 3A. 3B says, a wave pulse travels along the length of a string. Explain what happens when the pulse reaches the end of the string. If it is looped around a post and free to move vertically. So, looped around a post, we had this example in class. Basically, if the post is high enough, it'll move up, right, this string, and then it'll move back down, and the wave will get reflected back this way. Same amplitude, same velocity, as long as it's a perfectly ideal system, circular cow. And then if it's firmly tied to a wall, firmly attached to a wall, basically it's going to reflect, but then be inverted going this way. But same negative amplitude, I guess. Negative A, and this is going to be A. All right. Next question. Question 4 says a piano string is 1.1 meter long and has a mass of 0.09. Let me check that. 9 divided by 1,000 is 0.09 kilograms. All right. The fundamental frequency is 131 hertz. Okay. So question A is, what is the wavelength of its fundamental frequency? So if we know that the fundamental frequency is like this, basically, this is half a wavelength, and the length is 1.1 meters. So the wave, sorry, the wavelength is going to just be 2 times that, which is 2.2 meters. Okay, how much tension must the string be under if it is to vibrate at its fundamental frequency? So in this problem, I believe there is a relationship that we need to kind of have memorized, which is the velocity of a string is equal to the root of t being tension. Should put tension over this mu, which means linear density. Lin, I'll just put the p for density, whatever. Linear density, which is equal to mass over length of a string in this case. And this is also equal to just velocity, frequency times wavelength. So if we're solving for the tension, all we have to do is input values now. So mass over length, 0.09, 009, sorry, over 1.1, divided by tension, whatever. And then F in this is going to be frequency, wavelength. So I'll just multiply those together. So 131 times 2.2, that's frequency times wavelength, gives us 288. And then I'm going to square that because we're squaring this thing. And then I'm going to multiply it by 0.09 over 1.1. And I get a value for tension of, I believe this makes sense. Actually, that does not make sense, but 679 newtons, I believe. Let me also just expand my work a little bit just to make sure that's right. So square root tension over mu equals frequency wavelength. So tension equals frequency squared times wavelength squared times mass over length, mass over length. And I believe, it's the length of the string. That might be where I'm wrong. Okay. So the length of the string is 1.1 and the mass is 0.009. So, yeah, let me plug that in again. So the frequency is 131 hertz times the wavelength, which is 2.2 times 0.009 over 1.1. Still get 679, so I'm going to just assume that's the answer. If you get something different, comment down below. Yeah, I think this is going to be our answer for that question. And then, yes, that is it for question 4. For question 5, let's see, 5,000 hertz sound wave is directed towards an observer moving 3.50 meters per second towards the source. Okay, so I'm going to just go like, wow, 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 wow. That's source, 500 hertz. And then there's an observer. Yes, observer moving this way, 3.50. I'm gonna make a better zero than that. Meters per second towards them. So, we just use the, and then it's asking for the frequency of this reflected wave. So the frequency is just frequency times v of the wave. And then in this case, it's going to be added on to the velocity of the person. Because if we think about it, if you're moving this forward and this that way, whatever, like if you're moving a velocity and you're this object, you're going to feel the velocity of the combined objects. So we're actually going to be adding v object over v wave because this thing is stationary. And in this case, we're going to assume that v wave is 343 meters per second, which is the speed of sound at 20 degrees Celsius sea level, blah, 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 all that. Yeah, through air. And so, yeah, so basically, missed a zero. So then just plugging in values, 5,343 plus 3.50 over 343. Putting that into a calculator, 5,000 times 343 plus 3.50 346.5, 343. It gets us a frequency of, for A, frequency equals 5051.02 hertz. And so then let's see what problem B is. B is saying source is moving towards a stationary observer. So this time, let's see, stationary observer at speed of 3, 5. Okay. So we're going to use the same equation here. So it's going to be a little bit different. So we have V wave, and then V wave this time minus the velocity of the source. And so the reason why we have the subtraction here is if we think about it, we have the same situation of two things heading towards each other. It's still going to be faster for the person observing this wave, right? Like it's going to sound faster, but if we made this a positive value, basically that would make the perceived frequency lower, which would not make sense. So that's why we were basically subtracting it on the bottom. Basically, because it's on the bottom, I don't have a better explanation than that. So this is multiplied by frequency. So that's 5,000 times 343 over 343 minus 3.5, which is what? 339.5. Plugging that into a calculator, we get 5,000 times 343, 339.5, which gives us a very, very close number, not the same exact number. 5051.546,392. I don't know why I typed out all this. Hertz. All right. So that's that question. Let's see. Last question, question 6. A student is interested in determining the experimental value of the spring constant for a spring mass system oscillating in simple harmonic motion. Explain how period of oscillation and mass of system are related to the spring constant. So we have this relation, said period, and then spring constant mass. So the period is proportional to the square root of the mass. The period is proportional to the inverse of the square root of the spring constant. I think that's all they really want us to do. Maybe write it out in words. I'm not going to draw it out here because that's pretty difficult. Okay, so that's basically all you have to say. And the reason for that is if we flip this around and think about it, or if we just think about it here, if we increase t, this means m has to go down if everything else stays the same, or m has to go up if everything else stays the same. And if we increase k, t would have to go down. So yeah. Problem B says, explain how the student would linearize a graph consistent of frequency and mass data. So let's say hypothetically we have a graph of frequency and a graph of mass here. And I'm not even going to try and predict what the line would be. It's going to be some non-linear line, right? So we have to think of the relationship between this by setting up our equation again, k over m. And so we want to linearize frequency versus mass. So we see an issue here. It's going to be a inverse square root function, which I don't have the thinking capacity right now to think about what that is. I'll actually graph it because I'm a little bit curious now. It might just be like a parabola, but I don't have the brain power. No, that's a what? So 1 over x and then square rooted. Is that different from 1 over x? Okay, yeah, basically just like a steeper 1 over x graph with only one side. So basically we want to then linearize this to make it a straight line. So to do that, we want it to be in a y equals mx form. So we already know our y is going to be frequency. So I'm going to go into the next page. So y equals mx. And then we have 2 pi f root km. F equals root k over m. And so basically, m is our variable here. So if we set this up to look a little bit more like this, we get f equals, I'm going to put all the uh, constants on one side. So it's like m, and then our m is just going to be -1/2. I'll put that as a positive just so we can see the x a little bit better. A little bit confusing because we have m here and m here. This is two different m's. Our m here is going to represent the x, and our y is going to be the f. So what we're going to do basically to get a line between f and m is we graph m to the -1/2, or 1 over root m. I just wrote it like that, so then we can kind of see it a little better and won't get confused. But that'll give us a straight line. I believe it would be a negative slope. I'm not sure, but basically it'd be the slope would be root k over 2 pi. So yes, that's basically it. If I did any of these wrong, please tell me, because yeah, I'm just doing them like off the top of my head. I just got it sent into me, and I just wanted to see how long it would also take to finish these problems. 26 minutes. I mean, without explaining, I think it could go a little faster. I also might have done some of these wrong. That seems a little bit sus. That also seems a little bit strange. Might have read the question wrong. But please let me know if this was helpful or if I did something wrong. But thank you if you made it this far, and yeah, hope to see you guys soon for the test, and good luck.